Assalamu alaikum. My name is Mohammed Raad Hussein. Today we will talk about boiling nucleation during liquid flow in microchannels. Introduction. The boiling of liquids in microchannels microstructure is currently of great interest due to its very unusual phenomena and its many potential applications in wide variety of advanced technologies. Thermodynamic aspects of phase transformation of liquid in microchannels were analyzed to further understand the boiling characteristic and determine the condition under which a portion of such liquid is likely undergo phase change. A non-dimensional parameter of related criteria that determine the phase transition of microchannels were derived theoretically. The size of the microchannel resulted in dramatically high heat fluxes and superheats for liquid nucleation when the microchannels is sufficiently small. The boiling of liquid in microchannel and microstructure is one of the very important topics in this area, has unique significance in the development of the new technologies and devices of control of energy transfer and other advanced applications requiring very compact and extremely large heat flux heat exchangers. Bauer and Mudir experimentally investigated the boiling of liquid R1 in many channels and microchannels. They demonstrate heat transfer rated as high as 2 times 10 power 6 watt meter square in this channel and noted that the heat transfer and flow friction of pressure drop behavior indifference from the observed microchannels. Lane experimentally observed a bubble growth and boiling characteristic of microwire and microchip heater in microchannels. They found that it was extremely difficult to generate bubbles in microchannels. Pink and his co-worker have completed a series of experimental investigation on flow boiling through microchannels with rectangular cross sections. The experimentally measured boiling curve indicated that the boiling was initiated at a very low wall superheated of only 2 to 8 Celsius and immediately shifted to the fully developed nucleate boiling regime without evidence of partial nucleate boiling even for high subcooled liquid flow. However, it's sufficiently high wall heat fluxes and wall superheat which should be producing nucleate boiling according to observed boiling curve. No bubbles were observed in microchannel even with the assistance of the high power magnifying glass. It seems the size of the scale of liquid geometry may strongly influence in phase change transaction of corresponding flow mode. Two hypothetical concepts, evaporating space and fictitious boiling, were proposed to describe the explained physical process and fundamental phenomena. If the microchannel size is smaller than the evaporating space, then fictitious boiling it can be induced, otherwise normal nucleate boiling occurs. The evaporating space is necessarily space needed for evaporation. Fictitious boiling implies that the liquid has reached conventional nucleate boiling condition, but internal evaporating and bubble growth would be visual by ordinary means. The physical aspects of bubble generated and growth. Various investigators have demonstrated recently that the flow passage geometry has significant impact on liquid boiling bubble generation and bubble growth in microchannels. The concept of evaporating space suggests that there exists a minimum amount of space necessary to generate a vapor bubble in a confined microchannel. In fact, bubble size has long been considered as a critical parameter in understanding nucleate boiling characteristic and dynamic bubble process. The microchannels that are same size as the bubble embrace bubble indentation is physically restricted by the surrounding wall and the interior of the liquid on both ends of the bubble as shown in figure below. HSO investigate pool boiling characteristics of liquid and theoretically predict range of active cavity size of heated surface and the corresponding equilibrium bubble embryo radii. The corresponding bubble embryo size were around 0.16 thousand to 0.28 millimeter, and the average bubble diameter were about 0.15 millimeter. The fluid thermal properties are also expected to have significant influence on the activity cavity and bubble size. Thermodynamic analysis of nucleation conditions. Nucleate bubble boiling result from phase instability in liquid from classic thermodynamics. The phase stability condition of the pure substance include CV more than 0, and the equation below shows the delta P of delta V small than 0. Because CV is greater than 0 or virtually all substance, the thermal stability condition is satisfied and the equation is necessarily significant of the phase stability. Superheat of nucleated. For the wall superheated nucleation, also critical parameter and the characteristic of the boiling. In addition, the wall superheat can be related to the microgeometry using thermodynamic Maxwell relations. For a standard liquid equilibrium, the Caliburn equation can be substituted into equation 18 to give the approximate relationship. For a stable bubble embryo in equilibrium, the pressure difference across the bubble embryo delta P is given by the Young-Laplace equation. The pressure difference can be expressed as delta P equal delta PF to R over D. Combine the rearranging equation that show the final equation is delta T 480 V minus V over rho over H times D, where A is an empirical constant, previous experiment and comparison with result of Ln as shown at A to 218. Comparison experimental observation. Previous experimental investigation by Lin and Ping and his co-worker indicated that the microchannel size had significant effect on the boiling characteristic in microchannel. The nucleation criterion given by equation 6 provide the theoretical evidence of this experimental observed, even thought it may not given by exact limit. The critical nucleation heat flux predicted by equation 16 with C equal 1 is depicted in figure 2 of water, methanol, acetone, and R12. The minimum heat flux necessary to induce phase transition of nucleation increases rapidly as the microchannel hydraulic diameter decrease of specific liquid, and heat flux can reach dramatically high value of extremely small channels. Boiling nucleation in microchannel becomes sensitive to geometric size for microchannels that are several millimeters in size. For example, DH equal to 3 or 4 millimeters for water and methanol, and DH more than 2 millimeters for R12 and acetone. Conclusion. The boiling characteristics of liquid in microchannel were investigated by analyzing thermodynamics of fluid phase transition, consideration of the fundamental thermodynamics and interaction of bubble growth process and the microchannel geometry led to a liquid nucleation creating and dimensionless parameter that describe the boiling condition for liquid in microchannel. The predictions are in very good agreement with experimental observation of various investigators such as Lin, the author, and the co-worker, and reading it. The result also provide a theoretical and a quantitative basis of the evaporating space hypothesis and the nucleation in microchannel. More experiments are still necessary to understand the nature of the physical process and the substance, the theoretical conclusions. That's all. Thank you very much.